So if you want, we can now define another action, adjoint action. So we can define the small adjoint action on G tilde. And so it's given by, so it's an action of the Lie algebra on itself. So the adjoint action of T of A on T of C is given by commutator of TA and TC. And here we see that this is essentially given by F ACB, T of B. So if I look at this, what is it? This is some sort of matrix that is labeled by A, and we are taking the CB element. So we can think, so the adjoint action, which is an action from G tilde to G tilde, is a linear map, is a linear transformation, because it's represented by matrix. So let's formalize this. Let us define the matrix F of A and its CB element to be F of A, C, B. Okay? So these guys, essentially, these matrices FA form the adjoint representation of the Lie algebra G tilde. And they satisfy the Lie algebra, of course, otherwise they would not be a representation. Okay. So I haven't really given you a very explicit formula for F, but this equation should be very suggestive. And inspired by this equation, we define the adjoint representation F of A, so this is an A matrix, and C of D to be minus I F of A, C, D, okay? This is the definition of the adjoint representation. Now let's make some comments. See that, these guys, because, the indices here run from 1 to the dimension of the Lie algebra, right? Lie algebra of the Lie group. Therefore, the adjoint representation FC are dimension of the Lie group or the Lie algebra times the dimension of the Lie group or Lie algebra are matrices, right? So if I were to take, say, SU2, SU2, the defining representations, the defining representation is 2 by 2 dimensional matrices, right? But the adjoint representation of SU2 is going to be, will be given by 3x3 matrices. Because the dimension of SU2 is 3. And here we see that the definition of the adjoint representation is that the dimensionality of the matrices is equal to the dimensionality of the group or the algebra. Okay, so I think I have mentioned this before, but let me just, remind you that the notion, the dimension of a representation, is the dimension of the matrices representing the group or the Lie algebra. Okay, so the dimension of a representation is a different concept from the dimension of the group. Okay. So I have told you that, this, guys, like this formula is a representation of the Lie algebra. And I've kind of given you an argument why it should be, but I haven't really proved it yet, right? So we can prove this. But before I give you the proof, are there any questions?
Sir, could you explain the notation upstairs and downstairs and how it would make a difference? I'm a bit new to.
So yeah, when we defined the Lie algebra, when we talked about Lie algebra, it was TA, TB is IF of AB, TC. We had a choice. We could have written the C here, or we could have written the C here. It doesn't really matter. I just chose to write the C upstairs because I know that, the AB indices will be antisymmetric because the left-hand side is antisymmetric, right? So just to distinguish from the fact that AB and it's antisymmetric in the exchange of AB, but there is no antisymmetry between B and C or something, I chose to write the third index upstairs, okay? And that's it. I mean, the fact that I wrote I wrote the indices like this is to just have some parity with this, with the structure constant. There is nothing like deep about this. Like until we actually define a metric on our Lie algebra, we actually won't be able to give any meaning, intrinsic meaning to things which are upstairs or downstairs. Shortly, we will see that because of the adjoint representation, we will be able to define a metric on compact Lie algebra, which will allow us to lower the indices. Okay, Nahi?
Okay, sir.
For now, there is just to distinguish between the fact that the first two indices are antisymmetric and the others are not. Okay, any other questions? So let's show, we want to show that these matrices also satisfy the same Lie algebra.